welcome at Arktis. We are an high-tech company specialized in radiation detection and automation. And we are headquartered in Zurich. We are a full Swiss company. And we are here to show you a bit of our technology, a bit of what we are, and to run a couple of demos on two selected systems. One is a system for mobile radiation detection, something tactical that you can deploy on site in a very short time. And another one is a drone system. Arktis, as I said, we are specialized in radiation detection, but we also work a lot in collaboration with local agencies like the Civil Protection, the Arma Suisse, for instance, and the health department, the BABS. So all our systems are tested and taught together with some entities in a way that we can provide the customer with the best possible solution on the approach based on the application point of view. So we are present worldwide. Essentially, we have detectors and systems in each continent, and we collaborate with many radiation protection agencies. Each country has one, and each country requires some security levels that we collaborate with them to reach. The technology I wanted to show you is on this side is called flat panel gamma. We consider this a sort of a groundbreaking technology. It's done after something like 10 years of development in collaboration with many agencies, also DARPA, for instance, in US, and many projects together with the European Union, so Horizon, for instance. And this is made for creating a detector for gammas, which responds to most of the questions and the requirements of first responders and customs, especially in this case. So this guy here is made of plastic scintillators and is read out by solid state photomultiplayers, so what we call silicon photomultiplayers. Everything is manufactured by Arktis. Inside here, you don't see it, but inside here there are slabs of different sides of scintillators in order to have a uniform sensitivity to all the energies of interest for your applications. So we can guarantee the performance, and we can also guarantee the robustness of the system. And according to our contacts and interest from the end users, this system should solve most of the problems that we got submitted. Essentially, the difference between this and the standard devices is not using mobile parts, like for instance, the classic photomultiplier tubes, which are made of glass and metal. This one uses solid state sensors. Plastic instead of crystals, which is much better in the point of view of robustness, and dedicated technology. So instead of being something adapted from other applications, this is made for the scope. So it means that is the best possible sensitivity you can find for the specific application. At the moment, we use this detector for drone application. So we mount one of those things, a smaller one, on drones, and we run mapping, and we run special missions like finding orphan sources and something similar to this. And it has been deployed many times for demos and for pilot projects, and we have some systems in field as well. That's it. The main advantage, as I said, is that this system is generated to be immediately usable. So you have a system that is deployable in a couple of minutes, fully automated, with emissions that you just press start and it goes by itself. And so all the typical issues like piloting the system and getting data and analyze data is everything automated. This is a pretty general for Arktis products. Let's say that we try to make sure that the end users focus on their operation, not thinking and not being hindered by the system that we implement. And we do that because we want to be sure that once these kind of systems are in the hands of the end user, there are no issues related to integrating the concept of operation. This is particularly important in seaports, for instance, and in customs, where the concept operation is very well defined. So this technology, as I said, we use it for drones, and we are expanding the use of this technology because the advantage is also applicable to other applications and to all other systems like the radiation portal monitors and mobile systems we are working on. As I said, today we'll show you two systems. One is the drone, as I said. The other one, if you follow me, is the mobile system. We call it V2000. It's now prepared here, sitting on the floor. Essentially, this system is a gamma and neutron detector system, and is a mobile one, and is made for working as mounted into a vehicle, not necessarily fixed, can be put in the trunk and be implemented on site whenever you need. It can scan for radiation while moving in a truck. So you put on the back of your car and you use it, and it can be implemented as a portal. So the guys now are trying to mount it. It takes a few minutes. Essentially, the mounting process is made to be fast and stable. So the implementation of this can be done on uneven surfaces, and is thought to be deployed in situations like big events, even on grass, for instance, or on mud, or during situations like radiation accidents, or any kind of application where you are actually mounting a checkpoint for a small amount of time, like a few days, and then you have to dismantle it. We have two systems here in Switzerland, both by the civil protection, and they use it for doing, checkpoints at airports, for instance, or at borders sometimes. We had a trial with some of you, customs, a few years ago, on a system mounted into a van that is very similar to this. Actually, we use the same technology. You can imagine Arktis technology as sort of a building block. Our building blocks can be assembled together in order to generate a system that is fit for any scope you're interested to, especially in homeland security. So the technology you have inside, a user interface, and the way to use it is the same, essentially, from system to system, which is essential because every time you move from a system to another, you don't need extra training. You just work on the same user interface, but applicable to another operation. As you can see here, the system essentially is mounted like this. You see there is an overhead bridge. This overhead bridge is for guaranteeing a free lane, for instance, for pedestrians or for wheelchairs. And it can be mounted at the distance that you prefer. So essentially it can be used for pedestrian, but also can be used for cars or small vehicles in general. So this covers for a wide range of applications without necessitating of other systems. As I say, the deployment is very fast, and it comes with one or two detection units, as you see there, with or without the overhead bridge, and with an electronic box. There we usually put all the electronics for data collection, analysis, and power supply. One of those systems with an UPS can easily work for 8 hours operation without needing to be recharged. This is one of the reasons why you can use it on the way to the place where you're doing the checkpoint, at the checkpoint, and the way back on the same day without needing to plug it anywhere. which is critical, especially in cases where you are deploying the system in after an earthquake, for instance, where let's say the infrastructure is not guaranteed. Is connected Wi-Fi, so you can see the user interface without physically connect to the system and stay at a reasonable distance, or even 10 meters, without being forced to stay close to the detector. Same goes when you're using a car. You put in the trunk and you can see from the front seats the readings and the alarms and everything. So the system is in practice mounted already, ready, as you can see. It's deployable by 2 people in a few minutes. In the meantime, they finish this, I will show you the other device we want to show, which is characterized by the same type of features, like very fast deployable and very easy to manage. We are talking about the drone module that Pirmin is bringing here. Also, this one comes into a very robust box, so completely free from bumps and scratches and vibration. The device is commercially available, everything, starting from the drone to our detector. Can we zoom in? And is taught to answer to all the typical questions that first responders involved into radiation monitoring are asking for. It comes with a LiDAR down here to measure the distance in real time from the drone to the ground, and with the camera for having visual evidence of the findings. The detector here, as you see, is way smaller than the other, because one is made for ground operations and this one is made for airborne operations. And this drone, as I said, is commercially available. So it is not a prototype, that's a product. The drone itself comes with a set of batteries. Those batteries are characterized to be hot swappable. So in principle, if you have enough batteries, you can run a mission that can last for hours. Even though normally a drone can fly for 15, 20 minutes, the mission itself can run for hours thanks to these hot swappable batteries. Essentially, hot swappable means that you can replace the batteries without losing the power supply. The drone itself comes with a software, a navigation software that allows you to generate a map. And as you can see, perhaps here, running a small demo. Okay, you can see a map. You can navigate the system using GPS location. So essentially, you can plan your map and your mission beforehand. So when you go on a place of the mission, you actually can already be ready. So essentially, when the drone is in this level, so 2-3 minutes, you already have everything that you need for launching your mission. So time is essential, and this is what we try to do. The drone itself is connected to the ground station via Wi-Fi connectivity, and we can also provide an extra tablet, for instance, or an extra, essentially each user, even though is not driving, flying the drone or is not on site, even from remote, for instance, from the headquarters, they will be able to see exactly the same thing that you can see on site and in real time. This is also critical because when the mapping is done, if, for instance, there is no experts present on the site for the risks or for time implications, they can stay at the headquarters and support the local team in real time. So the system is, I think, both are ready. So we can show you right now a pre-recorded mission that we have done at Laborspitz some time ago. The mapping system here can record everything happening in real time, and then you can represent it again. After you download the data and information. Here you can see let's say the virtual drone, repeating the real drone mission, and populating the map with the count rates coming from the detector, and based on that, generating a heat map that tells you where the radioactivity hotspot, let's call it like this, the hotspot is present. Now, the typical missions that we have for this system is either mapping a wide area which is radioactive for whatever reason, like explosion of a dirty bomb, or to find and identify lost sources, for instance. This is a case where the radioactivity is diffused, but when we go for hotspots or for single sources, you can easily identify down to the meter where the source is. And this, with a single passage, the drone can do that. In a specific case, we were looking at 3.5 gigabecquerel of cesium source, cesium-157, and the drone was flying at 50-meter altitude and 10 meters per second. So a quite fast run, and essentially in real time, what you see here is the real speed of the drone when it was flying. So it can be done like this in a way that is very systematic, or can be looking for the highest radioactivity to investigate the specific spot. And critical for the responders could be the dose at ground level, and is measured and calculated thanks to the LiDAR that measured constantly the altitude of the system. So adapting the readings to the drone position and projected on the ground. And the camera that can snapshot the area that you are investigating to see if there is a visual presence of the sources or anything that is radioactive. The user interface, you can take a look. In general user interface, you can see a first page where you have the basic readings. It can be seen, but this is on a big screen for you, but actually you can see it on your mobile phone, for instance. You have the readings, you have the information about the alarm, you have information about the readings in real time, and the spectrum. The critical thing about this device is that it works exactly as the crystals, and it comes also with some identification features, but for a range of isotopes, which has been selected together with the end user to be the most common ones. So essentially, instead of having 100, 150 different radioactive materials into a library for a crystal, which is way more expensive than a plastic scintillator, we selected only a few which cover for essentially the 95% of the findings based on the experience. And based on that, we can provide a specific identification. So you have the information about the radiation levels, the visual position, the map, and also the radioactive material identified, which is essentially critical. Now we can say, if there are no questions, an interesting application for customs, I'll say, if you consider at the borders, there are always that long queue of trucks waiting for being allowed in the country. And essentially, if you use one of those drones to do a preliminary check for radiation, you can just fly high over the long queue of trucks, and based on what are the readings, you can pre-select trucks for a sort of a secondary inspection without slowing down your processes, without being involved into deviation from the lane and everything. So you can imagine this way, before a truck is even getting to your kiosk, you can already say this needs to be more investigated or not. And one of those missions will probably last 10 minutes or something like that. So this will strongly help the customs in their operation, adding the radiation monitoring that at the moment is not very common in Switzerland. you know something about happening in the south between Italy and Switzerland. Sometimes happens that some trucks have to drive back because of radiation. This will probably help these operations to be way faster than they are right now. Now, if we are ready for having a quick demo, we can show you how that they work. Essentially, we will pass through the portal with radioactive sources, and I'll show you how the portal reacts. And the sources we are going to use are very small. They are test sources, something that is actually called exempted. They can be freely shipped. Nevertheless, we can actually detect them easily and give you information about the dose level of the source and the type of source. That system there is featured with gamma and neutron detector. For now, we'll go with gammas. We have Paolo here that is crossing the portal. There you go. Back. Okay, so essentially what happened? He was passing through the portal set for cars, essentially, because it's very wide at the moment, with a very small source, as I said, the testing source, and the system was showing this much count rate over the natural background. The system recognizes the presence of a person passing through, thanks to the occupancy sensors, and the readings, anomalous readings over the threshold and over the background. This generates an alarm that is saved into the system and can be exported in real time everywhere you want. And it gives you also information about what has been found. In this specific case was an artificial source, cobalt-60, which is a common industrial source. We are not using any crystals, only plastic. So this is one of the unique selling points of our system. As I said, we can do this exactly the same thing with the drone, and they work in exactly the same way. So you can also show how the drone works with that. We will swap the screen to the drone. So you see, essentially, when you see the screen like now, you don't see much difference to what it was before, because the concept is to try to have the same user interface regardless of the system. So can we try it? Okay, so please go on the screen. There we go. So as you see here, the detector reacted pretty strongly at the point that you don't see the background anymore, because this system is supposed to be extremely sensitive, because they fly at high speed and high altitude. So to have a source so close is unnatural. But as you can see here, it's easy to verify the presence of a source and when it happened. This moving plot is in real time, as I said. And if we swap a bit down we scroll down with the user interface, we can also show how it looks like when it's detected by the system. Now, it's a sort of a spectrum where the information about the source is analyzed and the source is identified. As I said, everything gets saved into the system and at the ground and at any remote system that you would like to have. So essentially, if you have a remote station where a pool of experts are sitting there and waiting for alarms and to assess the severity of the alarm, all those information can be sent in real time. So time of essence, as I said, that will be the fastest possible approach. Now we have still a bit of time. So what about questions?
Yeah, so please, anyone for questions, just just to verbally, please.
Okay, in laboratory level, it's okay, it works, I see. How about coverages? As you have mentioned, there is a queue of transport of vehicles. If they have containers with metallic walls, at least 2 millimeter thick, how do you think, did you try this drone in that case? Will it detect radiation or not?
Yes, actually, we tried the drone. As I say, this is a commercially available system. So this drone has not been tried only in laboratories, but this drone has been tried also on field for real missions in collaboration with International Atomic Energy Agency, for instance. And then, let's say, the presence of the absence of a metal in between the source and the detector is always influencing it. As I said, a couple of millimeters. Essentially, a couple of millimeters of stainless steel will affect the low energy radioactive materials, as could be, for instance, cobalt 57 with a version of cobalt, or the americium source. But for how sensitive it is one, the only difference is the time that the drone has to spend over the specific track in order to collect data, but not for detection, only for identification. Because for what concerns detection, this system is extremely sensitive, has been tested with shielded sources, and as long as the shielding is typical, like the chassis of a car or the container of a cargo, it works perfectly. But the spectrum, which is affected by the shielding more than for the detection, is affected for the identification, then it will require a bit longer for giving you information about what exactly you are looking at. But in general, this is not the typical operation for the drone. Typical operation is to try to be as fast as possible in covering a large area, or to give you the typical first responder information, which is the radioactivity level, and if it's possible, information about what it is. And if the few seconds or the few, less than a second is not enough, the drone can just move back and stay for longer. When I say longer, I always talk about seconds, never minutes. So on this point of view, is perfectly tested. The other system is made for this kind of application, like scanning, say, vehicles. And so this is widely tested with various types of vehicles. Of course, when you come to containerized cargo, so the large systems where you have a big truck carrying more than one container or something like that, the problem there is to cover the entire area of the container to be sure that everything is tested with the same efficiency and the same accuracy. In that case, we, for instance, at the seaports, we use large systems. We can show you something from this. Let me please. This, for instance, down here is one pillar of our systems that are currently working in Antwerp, in Belgium. So the typical portal is made of 2 of these pillars covering for a single lane. And very important, they are compliant with specific standards, recognized worldwide. For instance, the IC standards for radiation portal monitors, or ANSI standards, American standards for radiation portal monitors. So this is that is very well regulated. And once we say our systems are compliant with the standards, it means that we are actually sensitive enough for covering for all the expected situations for scanning cargo and vehicles.
Well, thank you for your answer. For one more question concerning false alarms, as the drone is flying quite on high altitude, so probably there will be a lot of false alarms. And the question is about focusing on the object. Does your drone have special software which makes possible to focus on special objects, or does it cover all the area, including surroundings, woods, and so on?
Well, let's say that for what concerns navigation, the drone in this version doesn't have obstacle recognition. So he has to fly at an altitude where there are no hindrances, like, as you said, trees or buildings. No, this is up to the pilot, let's say. But for what concerns the false alarms, the drone works like this. It doesn't give you an alarm when it first goes on fly and start measuring the area. It gives you indication about the radiation levels that is reading. Then a secondary part of the mission will be for the user to select an area of the map for sort of a secondary inspection when the drone can fly lower, can fly slower, and start getting more dedicated information for the point of interest. But the drone itself is incapable to give you a false alarm. It does give you information about real level of radiation. Of course, when we set an alarm, we set also threshold for the alarm. So if we want to say, okay, we want to be informed by the drone with an alarm as the portals do, you have just to set up your threshold in a way that you are sure that you don't get any unexpected alarm, let's say like that. No? But this can be done easily, and you don't lose sensitivity. It's just a matter of knowing what you are looking for, essentially. Yeah? The false alarm rate is more applicable to radiation portal monitors, where you have something passing through, you have an occupancy, and during that occupancy, we are expecting a number of false alarm, like 1 over 1,000 occupancies, for instance, according to the American standards, or 1 over 10,000 if we go with recommendation from International Atomic Energy Agency. Okay.
Thank you for your answers, and other questions from my colleagues. I give floor to them. Thanks.
Okay, thank you, Pavel. But I have two questions. The first one, is it possible to combine your device with X-ray machines, particularly in the border cross border points?
Yes, actually, is it possible? The FPG, the flat panel gamma detector, is made also for solving this problem, which is one of the typical questions we get from customers worldwide. When you have an X-ray machine, radiation monitor, it gets crazy. It is obvious. But this system here is made with the technology that can work together with X-ray machines. And we already have a number of requests about that to implement our detectors together with X-ray machines. And it works like this. Essentially, this is an extremely fast detector. You can shut it down and turn it on at very high speed. In practice, it can work synergically with X-ray machines, especially the pulsed machines. You know, when you have the generator that pulses at very high speed, and this one can be synchronized with the X-ray machine at the point that when the X-ray machine is bursting a pulse, this one is off, and then back again. The current technology works the same way. Let's say the standard technology works the same way, but in that case, you have to manage a high voltage device, and which is extremely complicated. Also, for what concerns the efficiency, the sensitivity. This one is based on solid state sensors. This one actually can be sustaining the bursts from the X-ray machine without having any problem. So the efficiency of this detector is reduced by a very small amount, and is not affected by the X-ray machine. So in practice, this one can work in parallel with them.
The second question is related to the security for the person who discovered this radiation material in cargo. How you can use this information? What about the energy of our radiation, and who can discover or open or make secure this cargo after your discovery?
Well, let's say that the information you receive.
I have added something. When we started with our new border management in the beginnings of 90, in that moment, we found some of instrument with, for example, cobalt radiation from medicine equipment. In that moment in Poland, didn't exist no one similar to your device. Of course, in that moment, all these instruments were in the hands of our border guard. Today, we have many or various X-ray machines, but I don't know anything about this kind of instrument. And from this point of security is my question, because some of Polish customs officers were touched with this radiation bombs on other devices with radiation. I can say you that some of this kind of goods were in the pockets of your trousers. It was really very dangerous. But what about your instrument and how you can cooperate with the special services who can make with this problem secure?
Well, let's say that we have a feature called categorization. Okay, we can, when the system alarms, the system can tell you also about what are you looking at for what concern the radiation that is emitted, which is critical for the safety of the officers, and also about what exactly is the radioactive material. Now, it doesn't apply to all the possible radioactive materials, but you can imagine if you get an information that the source inside the box that you are trying to inspect is emitting the high level of radioactivity, getting this information from a system in real time, even before you get close to it, because it passed through a portal with our detector, or is a drone so far away from the operators. Then you can already select the right counteraction. If it's highly radioactive, you get close with more careful. If it's lowly radioactive, you can get close more confident. And when you have this information together with the information from the X-ray machine that tells you if the radioactivity coming from something that is heavily shielded, you can realize if it's a bulk metal or is not. Then you can also imagine if the source is inside this piece of metal, probably the radioactivity we are seeing now is way lower than it would be when you open the metal box. So these are all the type of information. Then when operators on site are connected with a pool of experts somewhere in the country, they can get informed in real time to which action to take. As I said, the medical is one of the problems because they are highly radioactive, they last short, and there are many, so it's very difficult to identify them. In the typical operations is once radiation portal monitors give you an alarm, then if the alarm is confirmed by the radioactivity level and stuff, then a secondary inspection modulated according to the readings of the portal is always due to have a final verification of the presence of which radioactive source, okay? But when you have X-ray machines and this type of system from Arktis, the only thing you can be 100% sure is that the X-ray machine is not affecting the readings. So when you have an alarm, you can be sure according to the false alarm rate that they say 1/1000 or 1/10,000, that inside the vehicle there is radioactive material. Now, there's also a matter of compromising between cost, efficiency, and and availability. Usually, for radiation portal motors, we use large plastic scintillators. They try to cover for very large areas, and this is the best choice at the moment, right? They can give you as many information as we can provide at the moment. We are, top notch from this point of view. But when you want to deal with materials like medical, then we usually suggest to have a secondary inspection with something like radiation identification device.
Thank you very much.
You're welcome. Any other question?
I would have one at a site that's affected with radioactive materials. You also find other materials like reinforced materials are there. So how far such another material affect or limit the detection of the drones, for example?
You mean at what distance we can detect radioactive materials?
Yeah. So when there's an area and you are working with first responders, these people are working at sites that are affected with radioactive materials, I assume. So these sites have some collapsed materials from different types of, composites as well. So there might be glass, there might be carbon fibers and stuff. So in such areas, how far such and other materials affect or limit the detection?
Well, let's say that it depends on the type of radiation we are trying to detect, neutrons or gammas. We are talking about gammas now, so we'll focus a moment on that. Let's say that high density material will affect the radioactivity levels. So usually, for instance, when we have a gamma source, we shield it with using lead, because lead is very dense and it can stop the radioactivity. So when you have like a collapsed building with the source underneath it, every material is contributing to the shielding. So even dust itself, when it's enough, can cover for radioactivity. But usually, I say when this kind of events, the sources that we are looking for are big, are a threat for the community, not small testing sources we are using now. So in principle, especially with the drone, if you are looking for a radioactive source under debris, is not much affected. If it's under metals, is way more affected. So let's say that depends what we find on the spot. But the general rule is higher the density of the material, the highest is the shielding level.
Okay, thank you.
You're welcome.
So maybe one more question if anyone had a question, Mike or anybody.
Okay.
Okay, we don't see any more questions now. So I think today we thank very much Arktis for this. Seems that it became a very interesting format to present things and to have discussions. So we'll be in touch soon about the possible making the video available, etc. Any final comments?
Well, we are super happy to have you here and to participate in this event. And I'll let you see the team for last time before closing. Pirmin, Chris, and Paolo, and show yourself. Pavel as well. It was our cameraman. And we invite you here at Arktis whenever you want. Pass by and you'll have a private tour to the company.
Thanks so much. I asked one more question. That did you show a map of Spiez in your radiations in the screen?
Yes, actually, that was Spitz.
Yeah, so that's my last note, is that our kickoff meeting of Penday in 2018 was 8 kilometers away from that location. So it's a small world. So thanks very much to Arktis today, and then we'll move to our next guests. Thanks a lot.